Okay, to start, let's review some of the basic tools that you probably encountered in your previous statistics classes. These are the building blocks that will comprise a great deal of the more complex methods that we'll use.
Mr. Simpson, how do you respond to the charge that petty vandalism, such as graffiti, is down 80%, while heavy sack beatings are up a shocking 900%?
Oh, people can come up with statistics to prove anything, Kent. 40% of all people know that.
I see.
We'll start with the summation operator. The summation operator, represented by the Greek letter sigma, is used as a shorthand to express a bunch of numbers in a set added together. For example, this expression basically means the sum of all x's, while this one would mean square all x's and then add them together. When we put a constant into the mix, the summation operator has some useful properties. So 5 added to itself 6 times is just 5 times 6, or 30. And when a constant appears next to a variable, we can pull it out of the summation operator, like this. Finally, summation operators also work with pairs of numbers, like this, or even sets of numbers, like this. Okay, with that notation under our belt, we can begin talking about descriptive statistics. The first attribute of a dataset that we'd like to describe is some measure of central tendency, or a typical value of a variable. The most common way of measuring central tendency is the average, or arithmetic mean. We typically use a bar to indicate a mean, so x bar here is the average value of variable x. We can also use summation notation to express the formula for the mean, like this. Okay, so the mean is useful, but there are other properties we'd like to account for. Take, for example, two groups of people. One with people all around the same age, and another with some very young and some very old people. These two groups actually have the same mean, 20 years old, but they have different levels of variability, or spread, or even noisiness. We'd like to summarize the variability of our data with just one number. How about the average distance between each data point and the mean? Turns out that this measure won't work. If we write it out in summation notation, and then simplify it using the properties of summations we just discussed, we learn that for any set of numbers, the sum of deviations from the mean is always 0. Intuitively, this is because numbers below the mean have a negative difference, and numbers above the mean have a positive difference, so their differences cancel each other out. We can get around this by squaring each difference before we add them together. So positive numbers stay positive, but negative numbers become positive. So if we square each distance before we add them together, and then divide by n, this gives us a measure called the variance. If we take the square root of the variance, we get another commonly used measure of variability, called the standard deviation. Another useful way to summarize data is by utilizing a histogram, which plots the frequency with which data points fall into certain ranges, or bins. By plotting a histogram, we can easily describe the shape of our data. For example, it might be bell-shaped, bimodal, skewed, or uniform. This is probably already familiar to you, so let's move on to the second major branch of statistics, inferential statistics. When we're doing empirical work, we have a population of individuals and certain characteristics of that population that we're interested in. These characteristics are called parameters. We could find the value of these parameters by examining every single individual in the population. This is what the Census Bureau does, for example. But most of the time, studying the entire population that we're interested in is difficult, if not impossible. The solution to this is to instead take a random sample of individuals from the population and compute their characteristics instead. These characteristics of the sample are called statistics. The goal of inferential statistics is to try to estimate or infer the value of the parameters we're interested in based on the values of the statistics that we actually observed. To do this, we first need to understand the idea of a sampling distribution. Because the samples we take are random, statistics are random variables. We call the distribution of all possible statistics from a given population the sampling distribution. Let's say we're wondering if Subway really is selling sandwiches that are 1 foot long as advertised. We buy 10 sandwiches from Subway, measure their length, and note the average. Then we buy another 10 sandwiches and get the average of that sample. If we were to do this over and over again and take a mean each time, the distribution of all the means from all the 10 sandwich samples would be our sampling distribution. Okay, what does this have to do with inferential statistics? Well, it turns out that we can know the shape, center, and spread of a sampling distribution of means so long as a few conditions are met. If we have random and independent sampling, plus either a large sample size or a normally distributed population, then we can know that the sampling distribution of means is normally distributed, or bell-shaped, centered at the population mean, and has a standard deviation equal to the population standard deviation divided by the square root of the sample size. This standard deviation of the sampling distribution is called the standard error. This is called the central limit theorem, and it's beautiful. Except, it doesn't seem that useful to us as it stands because of this formula for the standard error. To make inferences about the population mean based on the sample mean, we need to know the standard error of the sampling distribution. To know the standard error, we need to know the population standard deviation. And to know the population standard deviation, we need to know the population mean. So it might seem like we're stuck. But statistician William Gossett discovered a solution. Substitute the sample standard deviation for the population standard deviation. When we make this substitution, the sampling distribution is still centered on the population mean. The standard error is equal to the sample standard deviation over the square root of the sample size, and the sampling distribution takes a t-distribution with degrees of freedom equal to the sample size minus 1. The t-distribution is bell-shaped like the normal distribution, but has fatter tails and looks more and more like the normal distribution as the degrees of freedom increases. Okay, awesome. We're able to find out all the characteristics of a sampling distribution. Why does this matter? It might help to take a look at an example. Take this quote from great economist George Stigler. All great economists are tall. There are 2 exceptions, John Kenneth Galbraith and Milton Friedman. In addition to being a sick burn on Galbraith, Stigler's statement provides us with an empirical question. Are economists really taller than the general public? So, to answer this question, we fly out to the American Economics Association meeting in San Diego, tape measure in hand, and measure the heights of 16 random economists. We run the numbers and we get an average height of 68 inches, which is 2 inches taller than the average American height of 66 inches. So that settles it. Economists are taller than average. Well, not so fast. There's always the possibility that economists are no taller than average folks, and we just happen to get a sample of taller people just by random chance. What we'd like to know is this. How likely are we to get a sample with an average height of 68 inches or greater if the population mean is 66 inches? If it's really likely, then we can conclude that the sample just happened by chance. And if it's really unlikely, then we should doubt that economists are just as tall as ordinary Americans. Fortunately for us, we can answer this question if we know the characteristics of the sampling distribution, which, thanks to the central limit theorem, we do. So, first we need the standard deviation from our sample of economists, which is equal to 3.3. Next, we plug that into our formula for the standard error, along with our sample size of 16, to get a standard error of 0.84. So, if the average economist really is 66 inches tall, just as tall as the average American, then the sampling distribution will look like this. Taking a sample is kind of like picking a point at random on this curve. We're much likely to get a sample with a mean close to the center, and less likely to get a sample with a mean in the tails of the distribution. Based on the fact that 68 is pretty far out in the right tail of this distribution, it already looks like getting this result by chance is pretty unlikely. But we can go further and actually quantify how unlikely it is. To do this, we can use a t-distribution with a mean of 0 and a standard error of 1, also called a standardized distribution. Notice the shape doesn't change. We can now convert the mean of our sample, 68, into an equivalent value on the standardized distribution by subtracting 66 and dividing by the standard error of 0.84, which gives us 2.38. Using a computer can tell us that the area to the right of 2.38 on the standardized t-distribution is 0.0015. Since the total area under the curve is 1, we can make the following conclusion. If the true population average height of economists is 66 inches, then we'd expect to get a 16-person sample with a sample average height of 68 inches or greater about 1.5% of the time. This percentage, 1.5%, is called a p-value, the probability of observing our result if the population parameter really is 66. So, our t-test showed us that our results are unlikely if the population parameter is 66. This probability is low enough for us to rule out 66 as the value of our population parameter and conclude that the true population mean is probably greater than 66. The hypothetical value that we test is called the null hypothesis, and when we rule it out like this, we say that we are rejecting the null hypothesis. If we can't rule out a hypothetical value for a parameter, we say that we are failing to reject the null hypothesis. How unlikely is unlikely enough to reject? It can depend, but the most common criteria is that a p-value of less than 0.05 is low enough to reject the null. This corresponds to a t-statistic of about 2. If we reject the null hypothesis, we say that our results have statistical significance. We're testing the hypothesis here that the average economist is taller than the average person, but we can instead test to see if the average economist's height is different from the average person's. To do this, we look at the area to the right of 2.38 and to the left of negative 2.38 on our standardized t-distribution, which happens to be 0.03 or 3%. So our results are still statistically significant when we use two-tailed testing. One last thing we'll review from statistics is confidence intervals, which, rather than ruling out certain values for the population parameter, allow us to generate a range of values that have certain probabilities of capturing the true population parameter. For example, let's say we have a sample of 20 students and their GRE scores. From this data, we calculate a mean of 159.4 and a standard deviation of 4.2. Using the formula we previously used, we can find the standard error of this sample to be 0.94. Next, we need to know what range of values contain 95% of the data on a standardized t-distribution with 19 degrees of freedom. This table here contains those values. They're called critical values, or t-star for short. Using this formula, we can combine all of those numbers to calculate what's called the margin of error. If we add and subtract the margin of error from our sample mean, we create our confidence interval. We can interpret this one as telling us that there's a 95% probability that the average student's GRE score is between 157.4 and 161.4. To understand how confidence intervals work, think about a researcher taking 20-person samples over and over and over again and constructing a confidence interval for each sample. 95% of these confidence intervals will end up capturing the true population mean, which are represented in blue here, and 5% will miss it, represented by the red ones here. Confidence intervals and hypothesis testing are also closely related. If a 95% confidence interval contains a certain value, then a two-tailed test will also fail to reject that value at the 5% significance level. This works for other significance levels too. If a value isn't within a 99% confidence interval, it can be rejected at the 1% significance level.